Welcome back to Lecture 3. In the first segment of this lecture, we studied propositions in isolation. That is, we took one proposition and answered the question whether it was a tautology, a contradiction, or a contingency. In the second segment, we're going to study propositions in pairs, and we're going to ask the question whether this pair of propositions are logically equivalent or not. Now, here is the definition for this concept that we already touched upon in Lecture 1. Two propositions P and Q are logically equivalent if they have the same truth value for all possible assignments of truth values to their atomic propositions. Now, if P and Q are logically equivalent, we denote this fact with the following expression, where the three horizontal line symbol here denotes logical equivalence. Now, please realize that P and Q can be any arbitrarily complex propositions, not just atomic propositions. And so the definition of P and Q being logically equivalent simply means that whatever truth value you assign to the atomic propositions inside P and Q always turn out with the same truth value. They're either both true or both false. Now, it's important to realize that this logical equivalence symbol is not a logical connective like and, or, implies, and so on. So even though you write it in between two propositions, like this, it is still not a logical connective. And in fact, this expression here is not a compound proposition of propositional logic, the same way that P and Q would be. What this expression simply means is a summary of the English statement that P is logically equivalent to Q. And in particular, make sure you don't confuse this expression here with the one with a bidirectional arrow. P bidirectional arrow Q denotes material equivalence, whereas this expression denotes logical equivalence. These are two distinct concepts. Now that we have defined the concept of logical equivalence, we're interested in the following problem. Namely, given any two propositions, determine whether or not they are logically equivalent. Now the question here is, why do we care about this problem? Well, without getting ahead of ourselves, let's just say for now that when two propositions are logically equivalent, you're allowed to replace one with the other, and that will become very useful when we, for example, develop proofs. But for now, let's try to answer this question. In other words, is there an algorithm that will solve this problem, that is, given as input any two propositions of propositional logic? The algorithm should answer yes or no, these two propositions are logically equivalent or not. So can you think of an algorithm that would solve this problem? As it turns out, there's a rather simple algorithm that uses the concept of a truth table again. This algorithm will take as input two propositions P and Q. In the first step, it will build a truth table with one column for P and one column for Q. In the second and final step, the algorithm will compare these two columns. If these two columns are identical, that is, the entries in every single row is the same for the two columns, then the two propositions P and Q are indeed logically equivalent. On the other hand, if there are at least two entries that differ on one of the rows of these two columns, then the two propositions are not logically equivalent. Now let's trace this algorithm on a few examples. Now in our first example, the first input proposition is P exclusive or Q, and the second proposition is not P and Q or P and not Q. So the algorithm will answer the question whether these two propositions are logically equivalent or not. So let's build a truth table for both of these propositions. Since the only atomic propositions contained in both of them are P and Q, the truth table will again contain 4 rows. Now remember the standard ordering of the rows within the truth table as follows. And now we are ready to build the column for the first proposition. Since it only contains one logical connective, we can fill out the column right away using the definition of exclusive OR. Now remember that P exclusive OR Q is true when exactly one of the propositions P or Q is true. In other words, we have a true in the middle 2 rows here and false in the first and fourth rows. Now we turn our attention to the second proposition here. Since it is a disjunction, we first look at the first operand of the disjunction, which is a conjunction whose first operand is not P. So let's add a column for not P, which is simply the negation of the first column in the table. At this point, we are ready to compute the column for this conjunction, not P and Q. In other words, we are going to build the conjunction of this column and this one. Now remember that conjunction is true only when the 2 operands are true. And the only row where this happens is the second row here and here. Therefore, we have a true on the second row and false on all the other rows. Now let's turn our attention to the second operand of the disjunction, which is another conjunction. P is already taken care of in the first column, so now we need to add a column for not Q. Again, this is just the negation of the second column, like so. So now we're ready to build the next column corresponding to P and not Q. That is the conjunction of the first row, the first column, and this column. Again, the only row where those 2 columns contain a 1 is the third row, here and here. So we have a true on the third row and a false on all the other rows. Finally, we are ready to compute the truth values for the overall second proposition. Let's do that in the last column. Since this proposition is a disjunction, it is true whenever at least one of its operands are true. And that is the case on the second row here and on the third row here. So we have a true in the 2 middle rows and false on the first and fourth rows. And so in conclusion now, we're ready to compare the red column corresponding to the first input proposition and the blue column corresponding to the second input proposition. And since these 2 columns are identical, meaning whenever one is false, the other one is false, and whenever one is true, the other one is true, therefore the 2 input propositions are indeed logically equivalent. Let me make 2 comments about this logical equivalence. First, notice that the meaning of P exclusive OR Q is just P or Q but not both, which means if this proposition is true, that means either P is true and Q is false, or P is false and Q is true. So another way to translate this proposition is to say, either not P is true and Q is true, or P is true and not Q is true. So it's not surprising that these two propositions are logically equivalent. When you translate them in English that way, they actually have the same meaning. Now the second point I want to make, in case you're still wondering why we care about logical equivalence, well, the good thing about that is that every time you're tempted or you feel the need to use this expression, you could always replace it with this expression since they are logically equivalent. Now, why would that be a good idea? Well, the reason is because what it means is we don't really need this special symbol for exclusive or. We could always express the same concept, the same statement, by using a combination of not, and or. So what this means is that the exclusive or is not a necessary connective. We can always replace it with the combinations of the other ones. And that's a pretty useful piece of information. Now let's trace our algorithm on a second example, where the first input is P exclusive or Q, and the second input is P biconditional not Q. And remember, the first step is to build a truth table for these two propositions. Since they only contain two atomic propositions, P and Q, their truth table will again contain exactly 4 rows. Now let's look at the first input proposition. Since it's identical to the first input in the previous example, we can build the third column exactly the same way. So I'm going fast here. Now let's turn our attention to the second input. It's a biconditional with P as the first operand, which is already taken care of in the first column, and not Q as the second operand. So we need to add not Q as the fourth column of our truth table. And that's just the negation of the second column. Now we're ready to build the truth table for the second input proposition, P biconditional not Q. Now remember that a biconditional is true whenever its two operands have the same truth value. In this case, this happens on the third row and on the second row, as I just showed you, and now on the third row. In other words, we have a true in the two middle rows and false on the first and fourth row. Now the second step of the algorithm is to compare these two columns corresponding to the two input propositions. Since the red and the blue columns are identical, the conclusion or the output of our algorithm is that the two input propositions are indeed logically equivalent. Again, let me make 2 comments about this particular logical equivalence. First, remember the meaning of exclusive or. Is that the same meaning as this biconditional? Sure it is. Here's why. Remember, the biconditional is true when its two operands, P and not Q, have the same truth value. In other words, this biconditional is true whenever P and Q have different truth values, since not Q is the negation of Q. What does that mean, that P and Q have different truth values? That means one is true and the other is false, or vice versa. And that's exactly the meaning of P exclusive or Q. So again, it's not surprising that these two propositions are logically equivalent. Now the second comment I want to make is that, again, you're entitled to replace this expression here with this one, since they are logically equivalent. So we already knew we didn't need the exclusive or symbol because we could replace it with a combination of ands, ors, and nots. Well, it turns out you can also replace a single exclusive OR with a negation and a biconditional. That's another interesting fact to keep in mind. For our next example, let's go back to a point we made in an earlier lecture, namely the fact that a conditional and its converse are not logically equivalent. To check this, let's feed to our algorithm two propositions, namely the conditional P implies Q and its converse Q implies P. So the first step is to build the truth table for these two propositions. Since they only contain two atomic propositions P and Q, the table has 4 rows, as before. And in a third column now, we're going to build the truth table for P implies Q, which you already know by heart from the definition. P implies Q is only false when the premise is true and the conclusion is false, that is on the third row, and true everywhere else. Now let's look at the second input proposition. Q implies P. Again, that's a conditional, and it is false only when its premise Q is true and its conclusion P is false, and that happens on the second row, and it's true everywhere else. So in this case, what we notice is that the two columns are not identical. In fact, they differ on the second row and on the third row. So the output of our algorithm will be that the two input propositions are not logically equivalent. Remember that. A conditional and its converse are not logically equivalent, so don't confuse them. For our last example, let's go back to the exclusive OR. Let's feed as input to our algorithm the first proposition P exclusive OR Q, and as second input P or Q and not P and Q. So I will let you solve this one at home. In other words, make sure you actually go ahead and build the truth table for these two propositions. I give you the answer. They are indeed logically equivalent, but it's your job to actually prove it by tracing the algorithm. After you've done that, think about the reason why it would be the case that these two propositions are logically equivalent. Well, again, remember the meaning of P exclusive OR Q. It means that exactly one of P or Q is true, but not both. So what does this proposition mean? Well, what it means is, first of all, at least one of P or Q must be true, but also it must be the case that P and Q are not true at the same time. So of course what it means overall is that if at least one of P and Q must be true, but not both of them, it means exactly one of them must be true. And that is exactly the same meaning as this proposition. And that's why they turn out to be logically equivalent. Make sure you prove that by building the truth table. Before we conclude this segment, let's solve a puzzle that we encountered at the beginning of Lecture 2. Remember how we converted a couple of English sentences into propositions, namely S1 and S2. And at that time, the question we were interested in answering was, does S2 logically follow from S1? Well, you will pretty soon be able to answer this question, but for now, focus on this other question. Are S1 and S2 logically equivalent? In fact, the exercise that I want you to go ahead and complete right now is the following. Step 1, answer question 2. That shouldn't be too hard. You just practice the algorithm a few times. Please do it one more time with S1 and S2 as input. Then, as a second step, you will be able to answer question 1. And the hint here is you should be using your answer to question 2 to figure out the answer to question 1. So please pause the video and do your very best to complete these 2 steps. I will talk to you afterwards. Okay, now let's check your work. So for step 1, you build a truth table for S1 and S2. How many rows did your truth table have? Well, I'm sure you all built a truth table with 8 rows, right? Since S1 and S2 each contains 3 atomic propositions, C, E, and P. So, having done the truth table, what was the output of your algorithm? The answer to question 2 was, that's right, yes, S1 and S2 are indeed logically equivalent. So I trust that you did your very best to complete step 2. It wasn't as easy as step 1 because it wasn't as easy as just tracing an algorithm that we had studied in detail. You actually had to come up with something new on your own. So let's focus on step 2. My hint was you should use your answer to question 2. So to convince you that this works, let's move away from S1 and S2 for now, and let's take any 2 propositions, P1 and P2, that happen to be logically equivalent. What this really means is that P1 and P2 always have the same truth value. That is, they are either both true or both false. In every possible case, they always have the same truth value. So let's focus on the cases where they are both true. In particular, what it means is that since they're always true at the same time, whenever P1 is true, then P2 must also be true. But remember, this is just a definition. That's the definition of P2 logically follows from P1. And so what I just quote-unquote proved to you is that whenever any 2 propositions, P1 and P2, are logically equivalent, you can always conclude automatically that P2 logically follows from P1. Now let's just apply this general result to the specific case of S1 and S2. Since in step 1, we proved that S1 and S2 are logically equivalent, we can automatically infer that S2 logically follows from S1. And therefore, the answer to question 1 is also yes. So, to conclude this segment, we defined the concept of logical equivalence, and we discussed a simple algorithm that, given any 2 propositions, will answer yes or no whether they are logically equivalent. And finally, we used this concept to prove that the argument we discussed at the beginning of lecture 2 is indeed logically valid.